Hello everyone, welcome you all to PU News Hour. And today's session, we're going to have a topic on the recent developments in sustainable PU adhesives. This presentation will be given by Dr. Joseph Marcinko, who is President of the Polymer Synergies based in USA. And this event is hosted by Technobase. Let me quickly brief to you about Technobase so that you have an idea of what we are doing related to the polyurethane industry. Technobase is based in Thailand and Bangkok, established in 2005, and it is recognized as International Resource Center for Polymer Processing Industries and also Process and Manufacturing Technologies. So you can check all information about Technobase at technobase.org. A little overview about services and industry sector. We have two types of service. One is focused on the professional education, other one on the business services. As professional education, we do online training and also physical training programs. We also offer the executive diploma program, skill assessment, publications, and also various digital publications. And we have business services. We host exhibitions, conferences, virtual events, road shows, networking events, technical and business consulting, factory audit, and also the marketing and branding. When it comes to the industry or technology focus, of course, the polymer processing industry is one of the main activities of Technobase, and we are on the rubber industry, plastics, polyurethanes, adhesives, and coatings. When it comes to non-polymer side, energy environment, membranes and filtration, recycling and recovery, nanotechnology, and smart manufacturing and chemical processes. This gives you a broader information about what is Technobase, what we offer, and what kind of industries that we serve. And you always check our website, technobase.org. This is me, Peram Prasadara. I welcome you all. And if you have any questions on the Technobase or anything that we can assist you, please do contact me. Now, the tagline is join the journey of Technobase. So anything that you think our services fit in your business line or your education part of it, please join the journey. Let me quickly give you what we do for the PU industry, what kind of services Technobase offer. First of all, we have an exhibition, PU Tech Expo. We have rebranded. In the past, we have a PU Tech Asia, PU Tech Arab, PU Tech Africa. So we basically make it one single brand, the PU Tech Expo, focusing on the foams, adhesives, molding, and coatings. And it is a regional exhibitions for polyurethane industry. And every year we host in two different locations. In this year we have in Bangkok during the 29 to 30 March. And the second one will be the 21st to 22nd at 2023 in Sharjah. Sharjah is located near to Dubai in United Arab Emirates. You can always check more information about our expos at expo.technobase.org. I just give you, we are not new to the exhibition industry, we organize exhibitions. So these are our past exhibitions. We have hosted 5 exhibitions already on the PU Tech Asia. We did in 3 times in Bangkok. PU Tech Arab, we did in Sharjah, and we also have a PU Tech Africa in Johannesburg, South Africa. But this PU Tech Expo will rotate to different countries, different cities to reach out to the industry and serve the industry for the best. And we also have introducing the PU Meet. PU Meet is basically a local networking event. It's a one-day event where you can have a meet locally in the PU industry, get to know each other, at the same time update the new things happening in the PU industry. So we are going to host a PU networking meeting in Kuala Lumpur and also Jakarta in June. You can see 1 week you can go to 2 different locations. And also we're doing in African region in Nigeria, Lagos, and we have Kenya, Nairobi. So these are scheduled local networking events for the polyurethane industry. If you're interested, please check the details at the technobase.org. And we have this PU News Hour, like today you are joining. It's an online program on regular basis. We aim to be fortnightly, two times a month, that is scheduled. Please check our website, virtual.events.technobase.org. In this news hour, we'll bring the technologists or experts to give a talk on the latest trends when it comes to technical trends or market issues, or there will be some panel discussion. And also sometimes we will be hosting a called PU Clinic, where the experts will answer some of the questions you have. So feel free to post any questions you have. We will consider them in the future sessions of the PU News Hour. And we have PU Connect. This is basically a marketing assistance for the companies who wanted to use Technobase to promote their business. We offer both the digital marketing and also alternative marketing methods to promote your technologies, products, branding, okay, whether it is your supply chain as well as the products line also. And you can check our services details about it, marketing.technobase.org. There are very customized services also we're able to offer for the PU industry. And we have PU training as a professional education for the polyurethane industry. Currently, we have developed close to 25 online training programs for the PU industry, covering adhesives, general chemistry, and also foams, insulation. And we're trying to give. We're going to add more topics in the near future. You may check our website knowhow-webinars.com or technobase.org for further information on this. So that's about Technobase and what we are doing for the PU industry. If you have any questions, any concern, anything that we can assist you, please do reach out to me. I do encourage, again, please join the journey of Technobase, and I'm sure that it will be useful to you. Okay, welcome you all to PU News Hour. Today we have a session on the recent developments in sustainable PU adhesives. This presentation begins by Dr. Joseph Marcinko. He is the principal scientist and president of Polymer Synergies. He has more than 35 years industrial R&D experience, research management, and also is an active trainer and academic experience as well. His main interest and expertise are in the field of the polyurethane chemistry, biopolymers, adhesion science, wood composites, polymer characterization, and the polymer structure property relationships. So he has authored a number of publications, more than 50 peer-reviewed publications. He has more than 17 patents and many are pending. So it's a pleasure to have Dr. Joseph Marcinko for this program, PU News Hour. I invite him to give a talk on the recent developments in sustainable PU adhesives.
Welcome, everybody. Thank you for attending this Polyurethane News Hour put together by Param and Technobiz. We're going to talk today about the recent developments in sustainable polyurethane adhesives. I am Joe Marcinko. I'm the president and principal scientist of Polymer Synergies. And our headquarters and laboratory is in Bradenton, Florida, in the United States. The year 2023 marks the 86th anniversary of the introduction of polyurethanes by Professor Otto Bayer. Since its introduction 86 years ago, the global polyurethane market has grown, and it's worth over 106 billion. It's anticipated to be worth over $106 billion by 2025. And the reason for this growth is because polyurethanes are used in so many different applications, in construction, for thermal insulation, in automotive, in furniture applications, in coatings. It's used in a lot of different applications, so this is why it continues to grow. The isocyanates market, which is associated with polyurethanes market, is also estimated to grow at a rate of over 12% from the years 2020 to 2027. So this is a growing in a dynamic market. When we talk about polyurethanes, conventional industrial production of these polyurethane polymers relies on petroleum raw materials. Because of the volatility of oil pricing and because of growing societal and environmental awareness, there's been a large shift in polyurethane research towards replacement of these non-renewable raw materials with those that are derived from renewable resources, with the goal being sustainability. And if we define sustainability, Merriam-Webster Dictionary describes it as relating to or being a method of harvesting or using a resource so that the resource is not depleted or permanently damaged. The challenge of making polyurethanes more sustainable comes from the difficulty of replacing these non-renewable or non-sustainable raw materials with sustainable materials. This is more challenging for the isocyanate portion of the polyurethane than it is for the polyol portion of the polyurethane. There's been a lot of work done on sustainable polyols, and a lot of work continues to be done. And as a result of this synthetic chemical pathway being less challenging for polyols, there's a wide variety of bio-based polyols commercially available today from a number of sources. Before we get into the specifics of the sustainable polyurethanes, let's just review a little bit about polyurethane chemistry. And the reason this is important is because when I'm teaching about polyurethanes or when I'm designing products for polyurethanes, I do it from a structure property perspective. To get the performance that we want, we have to build the structure that we need to get the properties to give us that performance. So polyurethane reactions proceed via step addition reactions at the isocyanate double bond via an active hydrogen molecule, which means that the molecule has an acidic or an electrophilic proton, which once labile can initiate the reaction. And we can have OH groups, NH groups, and SH groups typical for polyurethanes. And what happens is we have an isocyanate that reacts with our polyol to form a prepolymer, and then we can chain extend it with low molecular weight diol to form a polyurethane. And this NH double bond OO is a urethane group, and we have a lot of those. That's why we call them polyurethanes. We can also extend this with an amine, a low molecular weight amine. So we have an NH double bond ON, which is a urea group, and we can have a polyurea urethane. So this is the basic chemistry that we are interested in. And if we think about that chemistry a little bit more, you know, in the absence of a catalyst, the positively charged carbon of the isocyanate in the NCO group is attacked by the nucleophilic oxygen, okay? And when we talk about nucleophiles, we're talking about things that donate free pairs of electrons. And so this particular reaction proceeds via a 4-membered ring to form our polyurethane product. This is still a matter of debate in polyurethane research, and there's a lot of work going on about how isocyanates actually react with polyols and other materials, certainly in the presence of different types of catalysts. So it's still an active area of research on the mechanistic perspective of how polyurethanes react. And I bring this to you because it's important to think about the chemistry. You can't design or formulate without thinking about the chemistry of what's going on. And this is why I put these introductory slides in to keep us in that mindset. Polyurethanes, of course, are phase-separated polymers. This phase separation and the unique properties of polyurethanes are the result of the molecular interactions and the incompatibility of the polymer components. So when we talk about the degree of order within the rigid domain, this will depend on the chemistry and the concentration of the isocyanate and the chemistry and the concentration of the chain extender. So are we using an aromatic or an aliphatic isocyanate? Are we using a diol or an amine as a chain extender? These things will affect the order of that rigid domain and the size of that rigid domain. The degree of order in the flexible domain will depend on the chemistry and the molecular weight of the polyol, and it'll depend on the degree of secondary interactions within the polymer network. So are we using an ester or an ether polyol? Are we using aromatic or aliphatic polyols? If we're using an ester, we're going to have much more hydrogen bonding, which is contributing to the network that we have in place in our polyurethane, because with the functional groups on the ester, we get more hydrogen bonds. This affects the degree of compatibility, this affects the order within the flexible domain, and it affects overall the polyurethane itself. So the phase separation and the chemistry which is associated with that phase separation is very, very important. And it's something to keep in mind when you're designing your adhesive system or your foam system or an elastomeric system for yourself. All right, when we talk about polyols, what are they? Polyols are macroglycols, so they're big alcohols, okay? And they're reactive compounds. They're typically liquids, and they contain at least 2 reactive groups. They vary greatly in structure and functionality and molecular weight. And the chemistry of the polyol and their molecular weight greatly influence the physical properties that you get for polyurethane. These are typical polyurethane polyols: polypropylene oxide, polyethylene oxide, polyethylene adipate. These 2 are ethers. This is an ester. And these are petroleum-based polyols, which are typically used in polyurethane chemistry. When we talk about polyols, they are the largest volume raw material used in polyurethanes. Okay, so cost and performance are the 2 biggest factors for determining the best polyol to use in your application. And the polyol's reactivity, based on the position of the hydroxyl groups, whether it's an ester or an ether, its linearity, its aromaticity versus aliphatic chemistry, these things all play a part in the performance of the polyurethane. And as you can see, polyether polyols are the largest volume polyols used, followed by polyesters. Then we have polytetramethylene ether glycols, and then acrylic polyols, and all of the others account for about 1%. And those are going to include some of the bio-based polyols I'm going to talk about in a moment. When we talk about new or sustainable feedstocks for polyols, lignocellulose is the world's most abundant natural polymer, okay? It has significant hydroxyl functionality, and thus it's a valuable raw material for polyol productions. Now, when we talk about lignocellulosic materials, they contain cellulose, hemicellulose, which is a less crystalline, less ordered form of cellulose, and lignin. These are the main components. There are also other minor components like tannins and resins and other types of extractives that occur in biomass. And when we talk about lignin, okay, we've all heard that it's a byproduct of paper making, and it's a very large byproduct of paper making. It's taken out of the process. And lignin in a tree or in a grass or in any other lignocellulose is the glue, the adhesive that holds together a lot of the molecules. It's what helps toughen this material. It's what makes wood such a strong, smart material as a living material. But it's also one of the contributors that makes wood very, very strong as a lumber, as a source of a building material. So lignin is a polyhydroxy material that has great potential for polyurethane feedstocks. If we talk about cellulose, using cellulose as a sustainable material for making polyols, there are a number of methods for making these polyols, and one of them is given here. It's a liquefaction and transesterification process, where we start with cellulose. We use ethylene or propylene glycol, a catalyst, to start to break up and functionalize this material, and then via transesterification, we can get to a polyhydroxy type of material of this type here. The references for all of these reactions you'll find on the slides that are given here, so that you can go and look at these references yourself. The drawback to this type of technology is that it relies on the use of solvents that are petroleum-based. That is changing as research continues. For example, the growth in biodiesel has increased the availability of crude glycerol, which is a byproduct of making biodiesel. And it's being researched as a viable alternative for ethylene and propylene oxides. So there are polyols that are available based on cellulose, and this is the method of how these materials are made. There's another method of using cellulose to make polyols, and that's oxypropylation. So in the presence of a catalyst and some caustic, the polypropylene oxide is grafted onto the lignocellulosic material under high temperature and pressure. And in contrast to liquefaction, when optimized, this oxypropylation is a chemical reaction capable of incorporating more readily available hydroxyl groups. So it avoids the solvent, and it's a grafting process, and it's another way of functionalizing biomass to make polyols. You're probably well aware of the polyols that come from vegetable oils, okay? So polyols derived from seed oils are widely available now. They come from the fatty acid components in the form of triglycerides. And here's an example of a triglyceride here, showing linoleic, oleic, and steric structures. So this is linoleic, this is oleic, and this is the steric structure of the triglyceride. When we talk about polyols that are derived from these fatty acids and triglycerides from different oils, they will vary in the fatty acid composition. For example, if we look at soy, this is the composition of the fatty acids, where it's very high in linoleic and oleic composition. If we compare that to soy, we see that oleic is higher than the linoleic, okay, but it's got a similar structure. And then we look at sunflower, it also has high linoleic and oleic. And so it's these double bonds that are functionalized that allow us to make our polyols from these fatty acids. Castor is very unique in that it is primarily racinoleic acid, which is already a functionalized polyol. And you can see that here. It's a naturally occurring polyester polyol. It's commonly used. It was one of the first polyols used for polyurethane chemistry, and it's still commonly used today, and it's already hydroxy functional. How do we make these polyols from oil seeds? Well, one process is ozonolysis. And in ozonolysis, we use ozone to form a ring structure off of the unsaturation in the fatty acid. Excuse me. And then it either goes through an oxidation or reduction to get down to our polyol species. But that's not the only method of doing it. Polyols from vegetable oils can be manufactured via epoxidation, hydroformulations, ozonolysis, as I talked about, air oxidation, and thiolene coupling. So there are a variety of different ways to get at polyols from these vegetable oils. When we talk about these polyols, they have good hydrolytic and thermal resistance due to their hydrophobic nature. And the unsaturation in ester groups make synthesizing these materials relatively easy. Another source for polyols is lignin. As we talked about, lignin is a multi-hydroxy natural polymer. It's composed of 3 types of alcohols, and you can see those alcohols in the different colors here. We have blue being synapyl alcohol, coniferyl alcohol is the green, and cumaryl alcohol is the red. And so these alcohols are what makes up lignin. And lignin is a beautiful molecule itself. A lot of research has gone on for decades with lignin because it is such a fascinating molecule. But the reason there's so much interest in it is because it's such a difficult molecule to break apart and to functionalized because it's a very concentrated network of these alcohols, of these aromatic alcohols. Lignin has been used in polyurethanes for a while in a lot of different applications. It's very good for UV blocking. It's very good for providing hydrophobicity. It's also very good for flame retardancy because it chars. And it's also used in self-healing polymers. So if it's used in a solid state, incorporated in a polyurethane, like a polyurethane adhesive, it could be used as a self-healing component, where if we get a crack in the polyurethane coating or adhesive or an elastomer, it can remend itself, and that's due to this polyhydroxy functionality of the lignin. Its utilization is limited because there are challenges of isolating the components of lignin, getting it to be homogeneous. It has a lot of heterogeneity, so we like materials to be homogeneous if we're going to use them in formulations. It has a tendency to aggregate because of its polyhydroxy functionality. There's a lot of steric hindrance, and it's got fairly low activity because of its network structure. But there is a lot of research going into lignin for use in polyurethanes. It can be liquefied by using polar solvents like THF and heat, and you can come out with a polyhydroxy material that's readily used in polyurethanes for elastomers, adhesives, and other applications. All right, so we talked about some sustainable polyols. We have to talk about the other side of the polyurethane, which is the isocyanates. And the most common type of isocyanates used are methylene diphenyl diisocyanate and toluene diisocyanate. And there are also a variety of aliphatic diisocyanates. This market is huge, and as you can see, MDI dominates, followed by TDI, followed by aliphatics, which is only about 4% of the overall isocyanate market. And the major producers are Covestro, Wanhua, BASF, Huntsman, Dow, Mitsui, and Tosh. When we talk about aliphatic isocyanates, there are 3 aliphatic isocyanates that represent greater than 90% of the total aliphatic isocyanates commercially produced. Those are hexamethylene diisocyanate, isoferrone diisocyanate, and 4,4-cyclohexane diisocyanate, which is the aliphatic version of MDI. Okay, HDI is the most widely used, accounting for approximately 50% of all of the aliphatics, followed by isoferrone diisocyanate, and then the H12 MDI. Almost 90% of these aliphatic isocyanates are used in coatings and adhesives. The advantage of aliphatic isocyanates is their superior weatherability. Anytime you have an aromatic group, it's susceptible to UV light, and it will yellow, and it will start to degrade. Aliphatics don't have that problem, and so this is why they're used in these applications. Aliphatic isocyanates are much slower reacting than aromatic isocyanates. So when you're formulating, that's an important factor to keep in mind. Because aromatics are filled with electrons, keep in mind that electrons are how chemical reactions occur. The more electrons you have around and available, the faster your reactions will be. Aliphatics are going to therefore be slower reacting as compared to aromatics. These are the 2 most common aromatic isocyanates used commercially: toluene diisocyanate, which usually is sold as a oligomeric mixture of 80-20, 2,4 and 2,6, and then MDI and polymeric MDI. 4,4 MDI or pure MDI is this structure here, and polymeric MDI is a mixture of oligomers that you see in this particular slide. I'm going to show you the composition of PMDI in this particular slide, and about 50% of the PMDI that you buy is 4,4 MDI, and the rest of it is higher oligomeric species, like triisocyanate is less than 30%, tetra is less than 10, penta is less than 10%, and there are still higher oligomeric species. Now, the reason I show you this slide is I told you earlier that when you're formulating, you should think about your chemistry of formulating your adhesive or your coating or whatever polyurethane you're formulating from a structure property perspective. So if you're formulating with pure MDI or 4,4 MDI, this is a symmetric molecule, and it's the smallest molecule in the PMDI mixture. So this molecule is going to react differently than this molecule, which is going to react differently than this molecule, which is going to react differently from the pentaisocyanate molecule. So they're all going to react differently. In addition to that, the size and the shape of these molecules will affect the order of the rigid domain, which will affect the properties that you're going to measure for your polyurethane. So these are things to keep in mind when you're formulating. The size and the shape and the reactivity of the molecule will affect the properties and performances. And if you take one of the other classes that Technobiz offers on isocyanate chemistry or formulating moisture cure adhesives or whatever, I talk in great depth about these types of structure property relationships. There are bio-based isocyanates. This isocyanate here is L-lysine diisocyanate. Okay, it's derived from L-lysine amino acid, and it's typically used for non-toxic biodegradable polyurethanes for pharmaceutical applications and tissue engineering applications, but it is a bio-based isocyanate that is available. There's an aliphatic isocyanate, pentamethylene diisocyanate, which is a relatively new bio-based aliphatic diisocyanate. I believe it was only introduced somewhere around 2015 or 2016. And it's primarily used in coating and adhesive applications because it's an aliphatic isocyanate. So you want to use it in applications requiring good solvent and weather resistance. And it can be used to replace hexamethylene diisocyanate. So it is a bio-based isocyanate that can replace hexamethylene diisocyanate. It's made from biomass, so it starts with the glucose from biomass. It goes through a nitrogenation process and phosgenation to form the pentamethylene diisocyanate. This is a technical data sheet of Desmondur Echo N7300. It is their version of pentamethyl diisocyanate. And you can see that it's got a NCO of approximately 22%. Its viscosity is fairly high, 9,500. And its bio-based content is approximately 68%. So it's pentamethylene diisocyanate is available from Covestro. It's also available from other sources that you can find for polyol suppliers. Like HDI, PDI is often reacted to form these trimer structures. And the reason this is done is to make these materials easier to handle. Okay, it also creates a trifunctional molecule rather than a difunctional molecule. But because the molecular weight has increased, these materials are much safer to handle and easier to use. So just like HDI is often sold as the trimer structure, so can the PDI. All right, we talked about sustainable raw materials. We talked about structure property relationships. Okay, let's start to talk now about sustainable polyurethanes. When we talk about polyurethane adhesives, they're highly versatile types of adhesives because they can be tailored for specific performance and properties. See, unlike something like polystyrene, you don't have one particular monomer which creates the polymer. So we don't start with styrene monomer. We start with styrene monomer to make polystyrene, but there is no one monomer for polyurethanes. And that's the reason why they're used in so many applications, because we can start with different isocyanates. There's a variety of different polyols, and we can combine these in various ways to give us the properties and the performance that we want. Now, the availability of bio-based polyurethane raw materials, mainly on the polyol side, allows for the tailoring of the properties to include sustainability in our structure property performance relationships that we're trying to build. And then, so these polyols from the biological sources or from carbon dioxide sources as the synthesis base provide additional benefit of these materials being less toxic and sustainable without detriment to performance. There are various types of polyurethanes that can be made. There are hot melt polyurethanes, there are reactive hot melt polyurethanes, there are solvent-borne, two-component reactive, there are water-borne, and one-component reactive polyurethanes. They all have the different bond strength development. Okay, so hot melts are going to be the fastest, followed by reactive hot melts. You have solvent-borne adhesives, which are going to be faster than water-borne adhesives, because solvents, organic solvents, volatilize much quicker than water does. If we see two-component adhesives, we have to build molecular weight by the polyurethane reaction product, forming our polyurethane polymer, and that takes time before it builds strength. And it's even slower for one-component material. So these are aspects of polyurethane formulation and development that have to be thought about. And the structure of the polyol and the isocyanate in your formulation is important in the development of these strengths. Here's an example which comes from this reference in Applied Adhesive Science, where there's a partial substitution of propylene glycol by a bio-based polyol. And there are various bio-based polyols that are being used here. And what happens, and what we're looking at here, is the thermogravimetric analysis. And you can see that the polyurethane reference is this first line here. And all of these bio-based polyols provide greater thermal stability, as shown here by thermogravimetric analysis. So that's an important aspect when you're formulating and designing. What environment is your adhesive going to be used in? And can I increase the thermal stability of the adhesive? And this is one way that it can be done, by using these types of bio-based polyols that are referenced here in this reference. They have some physical property data here, looking at the adhesion properties via a T-peel. And we can see that there are different amounts of these bio-based and CO2-based polyols that were used in leather to rubber joints. And this is the polyurethane reference. And you can see that these materials here have less T-peel strength. However, they do exceed the maximum requirements for these types of joints. In addition, the article talks about a shift in the failure mode. Okay, so although the strength may be lower, okay, strength isn't the only overall criteria that should be considered for designing an adhesive. You have to think about all of the factors that you want. So if you want sustainability, you have sustainability here because of these bio-based polyols that are being used, and they exceed the strength performance that's necessary. But also, if you can change the mode of failure, your overall performance may be greater. And so these are the types of things that you have to think about when you're designing an adhesive system. And what these bio-based polyols allow us to do is not only get the greater thermal stability, but form different types of network polyurethane structures, which can have an advantage in certain properties over others. And keep in mind, polyurethane chemistry and polymer chemistry in general, there's no perfect polymer and there's no perfect polyurethane. It's all a balancing act of performance and properties and cost and the things that you're trying to achieve in your adhesive or in your polyurethane. And so it's a balancing act that's based on the structures of the molecules that you're reacting. Here's some moisture-cure polyurethanes comparing conventional polyols with Crotia's preplast C36 dimer acid polyols. And they've been reacted with MDI. And we can see that they're comparing their periplast polyols, excuse me, with conventional PEG, PTMEG, and hexane diol adipate polyols. And you can see that lap shear adhesion to polyethylene is very good, and to polycarbonate it's very good. And it's reported that this good lap shear to these low polar substrates has to do with the hydrophobic nature of these C36 dimer acid backbones that they're using to make these polyols. Here's an example of some polyurethane dispersions prepared with bio-based succinic acid polyester polyols by way of N-methylpyrrolidone process. And the reference is given down here for Adhesive magazine. And you can see that storage modulus values differ when you're using the succinic acid versus typical adipic acid polyols. And we can compare the molecular weights of these. So the succinic acid 1000 has very high modulus. We can see that the rubbery plateau is much higher. And we can see that the thermoplastic drop is much higher than it is for these adipic acid material, okay? And the 2000 molecular weight is somewhere in between here. Okay, so these polyurethane films were made with succinic acid 2000. They have a dynamic modulus that's very similar to the polyurethanes made with adipic acid at 1000 and succinic acid at 2000. So, you know, again, here what you're looking at is molecular weight differences having differences in performance. So again, this is a structure property performance relationship, and here's an example of it. Okay, so there are other ways to make bio-based adhesives, and besides making polyols out of them. The protein hybrid adhesives are a form of adhesive there's a lot of research being done on, and it's being used in several different applications, a lot of them construction type applications for making composite wood and adhesives for those woods, for both interior grade and exterior grade products for construction and building and furniture. And the core technology is based on agricultural meals from these oilseed sources. So think about it. Not only can you use castor oil and canola oil and soy oil and sunflower oil to make bio-based polyols, you can take the residual meal that's there and you can make adhesives from that. So you can utilize 100% of these materials in different ways to make different types of adhesives. These agricultural meals all share a unique protein structure which allows you to disperse non-reactive oils or reactive oils like PMDI and protect that functionality. So if you think about these plants, okay, the seeds were holding oil. Okay, once the oil is extracted, the protein structure that was there to hold that oil is still within this meal, within these seeds, and that can be used to make a different type of adhesive. Currently, I'm in North America, so canola is used because it's not a food source, but it depends on the part of the world and what your resources are. But all of these can be used to make these type of protein hybrid adhesives. So these oil seed meals contain proteins and some other chemicals, carbohydrates and such, and cellulosics, which are some are water soluble and some are water insoluble. And the insoluble dispersible proteins are what we're going to use to make these protein hybrid adhesives. There are two fundamental aspects to this chemistry. You have the physical chemistry part, where you have the water-insoluble proteins that allow you to emulsify or disperse or compatibilize dissimilar materials. And this can be done for any of the oil seeds, soy, castor, canola. And then you have the organic chemistry side. And this is where we have water-soluble components and proteins that can react with isocyanates as well. So we have a physical and a chemical side to this chemistry. This is just a time-lapsed example of isocyanate in a dispersion of canola meal and water. So it's just this ground canola meal after the oil has been extracted, put into water at about 25 to 30% solids loading. You make this dispersion and you can put isocyanate in it. The isocyanate disperses very rapidly, and the isocyanate functional group is still present 2.5 hours after mixing. In fact, work has been done with these types of adhesives where this dispersion can be mixed and it can be used the next day as an adhesive. So it's very stable for long periods of time. It provides a lot of different advantages depending on the industry that it's being used in. Here I'm showing you it being used for making composite wood products, and what it does is it reduces MDI emissions. So a lot of times if they're making oriented strand board, they're spraying, atomizing PMDI onto the wood as the binder agent or adhesive. Okay, well, PMDI emissions are something that needs to be worried about in a manufacturing plant. So people are wearing respirators because this PMDI is being atomized. Well, if you use these types of protein hybrid adhesives, you reduce those emissions by almost 100%. Also, it cleans up with water instead of organic solvents. So there's a lot of different advantages that can be used. I'm just going to show you some data for boards that were made at the University of Maine. And we were measuring the properties of those boards. The important part is that we were able to reduce the amount of MDI 33 to 50%, 33% to 50%. So you can reduce the amount of MDI that you use by making these protein hybrid adhesives. And this is just an example of some of the data. This is the modulus of rupture. And what we're comparing here is a board made with 2.2% PMDI to a board made with 1.1% PMDI, so cutting the PMDI in half, and the remainder of the material is this protein hybrid, is this protein in water dispersion. Okay, so we can put it on and we can achieve the same modulus. We can also reduce the variability in the composite, and that's because we're putting a larger volume of material on and we can disperse it better. So again, you can make adhesives with isocyanates and proteins for various applications, and this is just one example that I'm showing you here. And all of the properties are better with the hybrid adhesive than they are with the PMDI reference alone. This is actually being used in certain commercial manufacturing facilities for making wood composites. All right, I've talked for a while, and I've talked about a number of different things. And the first thing we can summarize is that the use of polyurethanes continues to grow, and I see it continuing to grow in a lot of different areas. It's actually, you know, for example, with these protein hybrid type adhesives, it's expanding in arenas that weren't even thought about. And these are non-conventional type polyurethane reactions that you're getting. So it continues to grow, and the reason why it's growing is because you can tailor the polyurethane properties for whatever different application you want your adhesive to perform in. Sustainable polyurethanes are being produced because of the increase in bio-based raw materials. Certainly on the polyol side, there's a wide variety of bio-based polyols available, manufactured from different bio sources, as we talked about. Bio-based polyols are the leading sustainable raw material being used in these more sustainable polyurethanes. When designing an adhesive or polyurethane, please give thought to how the molecular structure affects phase separation and affects polymer properties. You should design your materials based on structure property relationships. And then these bio-based hybrid systems utilize isocyanates or polyurethanes as cross-linkers for proteins or other biomaterials that are being used in a wide variety of applications. So it's amazing the different applications that are being used. You know, for example, in medical applications, the use of lysine diisocyanate, also some emulsifiable types of aliphatic isocyanates are being used as cross-linkers for proteins and other types of materials, for adhesives, for tissue structures, and all types of applications. So isocyanates and polyols are very, very versatile materials that can be combined together, but they can also be combined with other types of bio-based materials to make new products and new types of adhesives. And with that, I'll leave you with a little bit about my company, Polymer Synergies. We're a unique provider of new technologies, of consulting services, technical training, and contract research and development. We specialize in polyurethane chemistry and adhesion science, in bio-based adhesives and bio-based composites. My contact information is here. Please feel free to contact me if you have any questions. And with that, I would be happy to entertain any questions that any of you may have.
Thank you very much, Dr. Joe Marcinko, for giving a good presentation on the recent developments in such as sustainable PU adhesives. The Q&A sessions, you know, what we are asking, you know, are people reach out to you, any questions they have, they can send an email to you, okay?
Okay.
Yeah. So any final remarks to the audience on the last, before we close this session?
I just want to thank everybody for participating. And I also just want to impart something that you heard me say over and over again during my presentation. It's very important that you think about the chemistry of the molecules that you're reacting with polyurethanes. Whether you're making an adhesive or whether you're making the foam, it doesn't make any difference. The polyurethane chemistry is the same. Okay, foams have blowing agents in them, but you're making an elastomer or you're making a rigid polyurethane, if it's a rigid foam, whether you're making an adhesive or a coating, the chemistry that you're reacting is the same chemistry. You're starting with isocyanates and polyols. And you should think about the structure of those isocyanates and polyols and how you want to put them together to get the performance that you need. So I encourage you to formulate from a structure property perspective.
Okay. Thank you very much, Dr. Joe, for being part of the PU News Hour and this very informative presentation on the recent developments in the sustainable PU adhesives. That's all, guys. Thank you for joining this session today, and we will be seeing you in the next episode of the PU News Hour. Please do follow on our website, virtualevents.technobiz.org. Thank you all. Bye-bye for now.
Thank you all.